Use cylindrical coordinates to evaluate the triple integral in this case. So let's start with the solid, okay? Z equals 9 minus x squared minus y squared. What does that look like? We've seen it a few times now, right? Your favorite surface, the paraboloid. So it opens down in this case, doesn't it? Where would I want to stop it? What plane would I want to stop it in? Probably the xy plane. So this bottom trace that I'm drawing would be in the xy plane. Where would this vertex be at? 0, 0, 9, yeah. 9 on the z-axis. So, okay. What would the equation then of this trace be? What would z equal at this trace? Since it's in the xy plane? 0. So what could you do to find the equation of this circle, apparent circle? Yes, but let's take one step at a time. So you would get 0 equals 9 minus x squared minus y squared. And so what is that? This curve in the xy plane is a circle. X squared plus y squared equals 9. Okay. So that's good to know, though, right? I'm not saying, I didn't mean to imply we're going to use this entire circle and its interior, the entire disk, but it's good to know the equation of that trace, isn't it? So if we want to draw what the solid Q in the first octant, well, what do we have to do? I suppose at the least we need a z-axis, don't we? And an x, at least a positive z and a positive x and a positive y, right? So z, positive x, positive y. And then I guess a good idea would be to draw maybe a trace that goes through the xz plane in the first octant anyway, well, borders the first octant, and the trace in the yz plane. And then we're kind of looking at Q as the volume of that weird wedge, aren't we? Or the solid, right? We're not finding a volume here, are we? Because the integrand is not equal to 1. So does everybody understand what Q is? That's pretty important, don't you think? Well, okay, then if you flatten it out, what is our region R going to be in the xy plane? Yeah, quarter circle, radius 3, right? So you flatten it out, and that's the quarter circle is the boundary. Of course, it's the quarter disk that is R. Okay, I think we're good to go. Let's set up our triple integral. Let's see. Cylindrical coordinates, right? So what is our volume element going to be? R dz dr d theta. R dz dr d theta, yes. And then, I don't know if I left enough room there or not. The integrand, what do we have to do with x and y and y again?
Pull a y out, and then the inside becomes x squared plus y squared, which can convert to r.
Yeah, that's a good observation. So if you look at that integrand, it's x squared times y plus y cubed. And a little time saver here, instead of making direct substitutions, x equals r cosine theta, instead of doing that, what if we factored out a y? And then we have the x squared plus y squared. And I think that does save us a little bit of time, right? Because isn't that guy r squared? Now we still have to plug in y in terms of r and theta. What would that be? R sine theta. Okay, so that's what we'll do. We'll say that our integrand becomes r sine theta, And then we have this factor of r squared here. And of course, I'll simplify that in the next step because there's another factor of r from the volume element. Everybody okay there? Okay, maybe you don't like it, but do you understand it? Maybe you're not okay with it, but you understand it. Okay. All right, so think floor to ceiling. So if you want to draw a picture of it, you could think of this as one part of the floor, the ceiling being the paraboloid. So what would the inner limits of integration be for z? 0 to 9. This is minus the quantity r squared, right? Minus the quantity x squared plus y squared, which is r squared. So 9 minus r squared. Make sense? Okay. What would r run from if you look down here? Our spoke would go from 0 to 3, wouldn't it? That's the radius. So 0 to 3, and then theta goes from 0 to pi halves. So there's your setup. And let's go ahead and evaluate it. So 0 to pi over 2, 0 to 3, 0 to 9 minus r squared, just copying all those limits, and then r to the 4th? Yeah. So r to the 4th, sine theta, dz dr d theta. Now, avoid temptation. Don't try and break up the integral here. You can't quite do it yet because you have a variable limit, inner limit, upper limit of integration, don't you? So you can't break it up into a product of 3 integrals yet. So avoid that. That's the dark side here. Don't turn to the dark side. So we will be able to do it after we evaluate the inner integral, though. Oh, boy. Jonas, we're going to have to put you, like, outside or something. I don't know. Outside? Yeah. We'll put your desk like, right outside the door. Now, I do have some good suggestions for you guys here. Don't put you're integrating with respect to what here for the inner integral? Z, right? So don't put the r to the 4th and the sine of theta inside the evaluation brackets. That's going to create more work for you. So leave them outside. R to the 4th, sine of theta, and then you integrate, 1, times 1, you can think of integrating that 1 with respect to z, you get z evaluated from 0 to 9 minus r squared, don't you? And then we still have the dr d theta on the outside. And so what does that become? Just a factor of 9 minus r squared where the z is? Because when you subtract 0, it doesn't do much. So you get integral 0 to pi halves, integral 0 to 3, still have r to the 4th, sine theta, and then times 9 minus r squared. Like that, dr d theta. Now, can you separate the function of, in the integrand, can you separate the function of r from the function of theta? Yes, so now, and the limits of integration are constant now on this double iterated integral that we've come up with. So now we can break it up into the product of 2 integrals. What would be the integral with respect to theta? What would be the integrand? That would be the sine of theta, wouldn't it? D theta. And then what would be the integrand with respect to r? The limits of integration, 0 to 3 on r, right? 0 to pi over 2 on the theta integral. Then we'd have r to the 4th times 9 minus r squared. What should we probably do with r to the 4th? Distribute 9r to the 4th minus r to the 6th. So, well, okay, let's handle the integral on the left first. What's the integral of sine of theta?
Negative cosine.
So leave the negative on the outside, and then evaluate from 0 to pi halves. We'll do that in the next step. Let's go ahead and integrate the other integral. What do we get? Let's see. It'd be 9/5. We're not going to get anything nice here. I don't think 9/5 r to the 5th minus 1/7 r to the 7th, evaluated from 0 to 3. Everybody with me so far? Okay, what do we get in this first integral? Cosine of pi over 2 is 0 minus cosine of 0 is 1. So we're going to get positive 1 there when the smoke settles, right? And then what do we get here? Nothing nice. Somebody already did. Is that all together? The- Okay, say it again. 4374 over 30. That makes sense because the common denominator would be 35. Okay, I'm going to take your word for it. Does everybody believe that? I mean, if you don't, just plug it in your calculator, right? Hit the fraction button. You guys know that. Okay. So that's going to be positive 1 right here. So just assuming that we have confirmation on that, we'll just stop here.